Hello there, and welcome to IQT's The Quantum Dragon podcast. My name is Brian Siegelwax, and I am the caretaker of the Quantum Dragon. My guests this episode are Oded Melamed, CEO of Quantum Source, and Nati Bar-Grinman, Director of Marketing at Quantum Source. Thank you both for joining me. Welcome to the show.
Thank you very much, Brian, and good morning.
Good morning. I've seen vacuum cells in neutral atom quantum computers, and I've seen photonic circuits in photonic quantum computers. But your technology involves a vacuum cell with a photonic circuit. What's the story behind taking two of the most popular modalities, neither of which has been mastered, quite frankly, and deciding to use them together? It has to be harder to use two, so what's the benefit?
Okay, so maybe we should go a little bit back. And I think that the audience is pretty familiar with the fact that quantum computing can be utilized and can be beneficial for the world only when large scale and fault tolerant quantum computers are available. We strongly believe in the photonic approach because of its ability to scale up relatively easily. However, the traditional photonic approach has some drawbacks, and the major drawback is that generating the qubits and creating the entanglement between the qubits is done today using probabilistic processes with a very low probability of success. Each and every photon in such photonic clusters that are used in the photonic quantum computation is a result of millions of attempts. This is why when you see illustrations of how large 1 million qubit system will look like, it looks like a big fab at the size of a few football courts, requires energy like a small city. And this is something that we would like to address. And our technology, which combines photonic qubits and atomic qubits, resolve one of the key bottlenecks of photonic quantum computation, which is this probabilistic process. And using this combination, we can generate the photonic qubits as well as to generate the entanglement between the photons using deterministic process. Now, this deterministic process is about 4 orders of magnitude better efficiency compared to the probabilistic process. And this is our secret. And we are the only company in the world, as you mentioned, that combines photonic qubits and atomic qubits, and we are doing it just for that reason, deterministic generation of the qubits and the entanglement process.
Heard that before, that photonics is relatively hard to start, but relatively easy to scale, whereas the other modalities are relatively easy to start and relatively hard to scale. So I have heard that before. I am a big fan of analogies, and you've got a great one. You already started mentioning you use atomic qubits with photonic qubits for photon generation and entangling, and you use a sewing machine analogy, atoms acting like needles in sewing machines, stitching the photons together into 3D cluster states. For those who don't know, what is measurement-based quantum computing? What is 3D measurement-based quantum computing? And for everyone, why did you decide to go that route instead of the more familiar linear optical route of Quandela, Xanadu's X series? And also, why
Mhm.
3D? I haven't seen that anywhere else.
Okay, so first let's start with the measurement-based quantum computation, which is also called the one-way quantum computation. So basically, with measurement-based quantum computation, you can separate the computation into two stages. One stage is associated with creating a large entangled resource state. And the second stage is related to performing computation via measurement only. Um, and the measurement is done by choice of the measurement basis. And then the output of the measurement is fed to a classical computer, which determines the algorithm and the next set of measurements. So what are the advantages of measurement-based quantum computation? The key advantage is that we can decouple the entanglement generation from the actual computation. So all the entanglement is created up front, and the computation becomes just a sequence of measurements. So why this is important? It is important and it matters for photonic quantum computation is that we can optimize the entanglement generation and the computation independently. And that's a huge advantage for any scaling. Now, with photons, photonic quantum computation and measurement-based quantum computation are have a perfect match. Um, Photons are excellent flying qubits. You are sending the qubits through the fibers of waveguide, and they preserve their state, but they are poor in terms of gate qubits. Now, the photonic qubits move at the speed of light. That would either they would either fly very, very fast or get lost in the delay line before you could even do anything meaningful. So doing circuit-based quantum computation with photons is almost impossible. So it's like the um, the natural choice for photonic quantum computation is to use measurement-based. Now, regarding the 3D construction of the resource state of the or the cluster state, that is one of the key benefits of photonic quantum computation. So with quantum computation, basically you generate small clusters of entangled states, and then you stitch them together into a larger cluster. But what is also possible to do with photonic quantum computation is that we can stitch or combine clusters that were generated in different time. And we are doing it by providing to the stitcher or the fusion gate photonic qubits that were generated in different time. And to do that, you just need to send one of the qubits through a long delay line, which is fiber, which acts like a quantum memory, and then get to the stitcher or the fusion gate qubits that were generated in different time. So this is only possible with photonic quantum computation, and that's one of the key advantages. So if you want to build a 1 million qubit system, with this architecture, basically you don't need to generate all the 1 million qubit at once. You can generate this task over many, many clock cycles.
Yeah, I've noticed with the linear optical route that photons are like teenagers. They just do whatever they want and go wherever they want. You claim that your tech does not use cryogenics. Photonics
Mhm.
is famous for claiming that, but then we find out that the detectors and or sources use cryogenics. But I do know that room temperature, everything is in the works. So is your tech truly room temperature?
So 99% of the system is room temperature. So the photonic generation, the entanglement process, everything is done in room temperature. The only part in the system, which is about 1% of the bill of material, is just the output detectors. The single photon detectors, which their output is fed to the classical computer, requires cryogenic temperature because they work efficiently only when the temperature is very, very low. But there is a clear separation between the complete system that generates the large cluster states and the output detectors, which again are only 1% of the bill of material and also can be placed in a different location.
You didn't mention any names, but when you talk about physical scale, you're obviously poking PsiQuantum and Xanadu. So compared to their warehouse-sized systems, what is the projected physical footprint for your million qubit system?
So the physical area that will be needed for a 1 million qubit system is about 1,000 square meters, um, which is not very big server room.
Um, Last question I have.
Mhm,
Your modules are named Origin, which makes
mhm,
sense when your company name is Quantum Source. But considering how overused the name is, and this is more a critique of the industry, it's the
mhm.
name of a company, it's the name of a software. Are you giving any consideration to changing it, perhaps to a synonym of Origin? Because again, the name makes sense for you, but someone searching for Origin is likely to find this other stuff.
So the name was picked by our employees. We gave them several options, and that is what they liked. But Brian, you are welcome to suggest our next generation system name.
I am taking note of that. Although, to be honest, I'm actually terrible with that. I totally lack imagination, and most of the ideas I have are stolen from someone else. Like something you say plants a seed in my head, and that turns into all the wacky stuff that I write. But I did make a note about it, so I'm going to see if I can come up with something better. I'm going to challenge myself.
So you have about 1 year to think about the
Okay,
name. Propose it to Nati.
1 year deadline. I'm making a note. Yeah, there are a lot of names out there that are, I won't go naming all of them, but quite a few that when keep reading about the industry and writing about the industry, certain names just keep popping up over and over again. And our Origin, again, if one company uses it, I would say it matches yours the best, but it is out there. People like it.
Mhm.
But that was my last question, so the floor is now yours. You can say anything you'd like.
So in Quantum Source, we develop a unique technology. As I mentioned, we are the only company in the world that combine photonic qubits and atomic qubits. And we enjoy the benefit of both, the scalability of photons with the ease of entanglement of atomic qubits. With this technology, we can really change the world, build a large-scale system with millions of qubits at the size and cost which are reasonable. Um, so join us for this adventure and this journey towards changing the world of quantum computation.
Sounds good to me. So, thank you again for joining me on IQT's The Quantum Dragon podcast. And thank you to everyone who is still listening. There are links in the podcast description for more information. And as always, feel free to stick around for the outro music. It's called Dungeons and Dragons. Enjoy.